Hey everyone. One of the most common applications of derivatives is in displacement, velocity, and acceleration. So we're going to go through an example showing just that. Now, say you got a jetpack. How cool would that be? And you stood on the edge of the Grand Canyon, and then you went into it, and then you were like, phew, and you just went off into space. It would be so fun. And say that your vertical displacement from the canyon rim, so like the canyon rim would be 0, anything below that would be negative, above it obviously positive. So say your vertical displacement from that canyon rim is this equation here. So if you were to look at the graph of that, and this would be in meters and seconds, the graph looks like this guy right here. And as a really quick sketch of it, let's put a shirt on our little jetpack man. So you have this graph in meters and seconds. So if we did the derivative, we took a tangent line and we looked at the slope of that line, the units of this would be meters, change in y, over seconds, the change in x. Meters per second. Oh wait, that's velocity. So the derivative of the displacement will give us our velocity. So let's find that derivative. So v is y prime, which is, using our power rule, 4x cubed minus 15x squared, because we have 5 times 3x, 5 times 3x squared for the derivative, plus 7, there's a squared on that, plus, oh, I lost that square at the start and it threw me off. It's important, this is a good lesson. When you're writing things down, check your work. Okay, 14x is the derivative of 7x squared, and then minus 4. So if we were to look at the graph of this guy, the units of it, the units of y would be meters per second. I'm going to take the shirt away. We would have meters per second for y, and we'd have seconds for x. I'll show you that graph in a moment. So if we looked at the derivative of the velocity, so our second derivative of the displacement, that will give us, and this, by the way, is a cubic. It looks something like this. But if we looked at the derivative here, we would end up with meters per second over seconds, meters per second, and that is acceleration. So the second derivative of displacement, or the derivative of velocity, gives us our acceleration. So our acceleration is v prime, or y double prime, and we get 12x squared minus 30x plus 14. So having our original function, then our first derivative, second derivative, we can tell a lot of what's going on. Here's all 3 graphs together, and I know this is a lot to look at. So in blue is the original quartic function. In red is our first derivative, the cubic, and in black we have the acceleration, which is quadratic. If you took the derivative of acceleration, by the way, it hardly ever comes up in the real world, but just for fun, if you were to do it, that actually has a name too, and it's called jerk. And it's basically, if you consider, like, knowing acceleration is your change in velocity. If you suddenly change your acceleration, like if you're in a car and you're like, say you're slowly just hitting the brakes, but then a dog runs out and you really slam the brakes on and you feel that kind of jerking sensation, that's that sudden change you feel in your velocity, which you feel like physically in your body, and it feels like a jerk. So that's why it's named that, I think. So the things you can figure out from this, we're going to look at 4 different times. 1, 2, 3, and 4. So at time 1, your location, -1, so you're below the rim of the canyon. You have a velocity of -1, and that's in meters per second. And then your second derivative is -4 meters per second. And that sounds super weird. And so what does that mean? So you have a negative velocity. Well, a negative velocity just means you're going down, not up. Or if you're talking about like left and right motion, it might mean it's left, not right. So a negative velocity is possible. It's totally fine. It's just a direction. If we're talking speed, your speed would be 1. You can't have a negative speed. Speed is simply the absolute value of velocity. Let's write that down. So when people consider speeding up and slowing down, you want to look at both your acceleration and your velocity at the same time. So like if you have a positive velocity, like at time 4 you have a 68, or time 3 your velocity is 11 meters per second. If you have an acceleration of 32 meters per second, that's a really fast acceleration, by the way. But that would mean that you are getting faster. Seems reasonable, right? Because your change in velocity is positive, you add that to a positive velocity, so you're getting faster. If you have a negative velocity and a negative acceleration, that sounds super weird, but if you think of that as you have -4 meters per second. So like if you have -1 for your velocity right now, in 1 second, your velocity would be -5. And that is more speed, the absolute value. So if your velocity and acceleration have the same sign, essentially they're working together, so you're speeding up. So if velocity and acceleration have the same sign, positive or negative, you're speeding up. If your velocity and acceleration have opposite signs, you're slowing down. You can think of those as working against each other. Like at time 2, I have a velocity of -4 meters per second. So then a second later, if this was constant motion, my velocity would be -2. And a second after that, my velocity would be 0. That means I have less speed. So I'm slowing down. So if your velocity and acceleration have opposite signs, you're slowing down. And if you're ever asked to justify, are you speeding up or slowing down? This is all you have to say. I'm speeding up because V and A have the same sign. I'm slowing down because V and A have opposite signs. Think of them as working together or against each other. So if you need to find velocity, acceleration, and you have displacement, you derive again.